Today we are going to deal with the effect of viscosity on fluid flow, explain the basic concepts of laminar flow, turbulent flow, critical velocity, and Rynolds number, and its application in fluid flow problems. All fluids existing in nature, both gases and liquids, are viscous and compressible. In the 18th century, scientists sought to specify the motion of fluids by mathematical relations. These relations could be developed only after certain simplifying assumptions were made. The fluid was assumed to be non-viscous and incompressible. Such a fluid, which in addition had no surface tension, was called an ideal fluid. Generally, liquids are said to be viscous but incompressible, whereas gases are said to be compressible, having low viscosity. For example, water is incompressible, but air is compressible. Viscosity causes shear stresses in moving fluids and hence loss of energy. All real fluids resist any force tending to cause one layer to move over another. This resistance to the movement of one layer of fluids over an adjacent one is due to the viscous nature of the fluid. Viscosity is therefore defined as the property of fluids by virtue of which fluids resist relative motion between adjacent layers. Without viscosity of fluid, there is no fluid resistance. Viscosity is greatly affected by temperature. Viscosity of liquids decreases with temperature, while that of gases increases with temperature. Consider this oil and water. The oil is more viscous than water. A fluid particle in motion is subjected to viscous force, pressure force, and gravitational force. Viscous forces play an important part in many fluid flow problems, such as flow in conduits, flow through porous media, the problem of lubrication, design of turbines, water distribution systems, pipe network in chemical industry, irrigation canals, aircrafts, missiles, etc. Till the middle of 19th century, scientists and engineers obtained much information about the flow in pipes and open channels through observation and experimentation. This information was entirely empirical because practically nothing was then known about the laws governing the influence of viscosity. Osborne Reynolds was the first to introduce viscosity as one of the parameters in the analysis of fluid flow. Osborne Reynolds, 1842 to 1912, came of a clerical family in Belfast, and after workshop experience studied mathematics at Cambridge, where he graduated with honors. In 1868, he was appointed to the new chair of engineering at Owens College, which later became Victoria University in Manchester. He was elected a Fellow of Royal Society in 1877, and he remained active at Manchester until his retirement due to failing health. Rynolds' interests were manifold, from that of problems in mechanics, thermodynamics and electricity, to problems in navigation, rolling friction, and steam engine performance. Rynolds' approach to the solution of problems was primarily that of an engineer. While the existence of two types of flow, called laminar flow and turbulent flow, was known before Rynolds. He was the first to publish a paper in 1883 formulating a parameter to take into account the effect of viscosity. This parameter now bears his name and is called Rynolds number. The apparatus used by Rynolds for conducting experiments was basically as shown. Water from the tank could flow out along the glass tube at a rate controlled by a valve at the outlet end. A fine nozzle connected to a small container of a liquid dye is used to discharge a colored filament in the flowing liquid. If the velocity of water remained low, the filament of dye would pass down the tube without mixing with water. Such a flow was called laminar flow. As the velocity of water increased, this type of flow would persist until the velocity reached a value at which the stream of dye began to waver. Further increase in velocity of water made the fluctuation in the stream of dye more intense, particularly towards the outlet end of the tube, until a state was reached in which the dye no longer traveled the whole length of tube as a distinct, unbroken thread, but quite suddenly mixed more or less completely with water in the tube. Such a flow was called turbulent flow. Still further increase in velocity caused no alteration in the type of flow, but the dye mixed even more readily with water, and complete mixing was seen nearer the inlet end of the tube. Laminar flow, in which the dye remained as a distinct streak, could be restored by reducing the velocity. Although Rynolds used water in his original tests, subsequent experiments have shown that the phenomenon is exhibited by all fluids, gases, as well as liquids. Moreover, these two types of flow can be found in all situations and is not confined to circular tubes alone. Now, let's go to the hydraulics laboratory to demonstrate Rynolds' experiment. This apparatus is similar to the one used by Rynolds in his experiments. This is the tank containing water. The baffle plates reduce any disturbance in the water. This is the dye container, which injects a fine jet into the stream at the bell-mouthed entrance. The flow in the long glass tube is controlled by the outlet valve. To measure the discharge, from which velocity is computed, a measuring tank is used. The main supply valve is opened and the tank is filled with water, with outlet of glass tube partly open so that no air is entrapped in the glass tube. The outlet valve of glass tube and the inlet valve of the tank are closed when the tank is full of water. Now, we wait for some time to allow water in the tank and the glass tube to come to rest. Now open the outlet valve of the glass tube so that the velocity of flow is very small. Also open the dye injector so that the dye is admitted into the bell-mouthed entrance of glass tube. We find that the dye appears as a straight line extending through the glass tube. This type of flow, in which fluid particles move in an orderly fashion, is called laminar flow or viscous flow or straight line flow. Let's increase the velocity of flow with the help of regulating valve. We find that the liquid continues to flow in laminae until the velocity of flow reached a value at which the stream of dye begins to waver towards the outlet end of the glass tube. Further increase in velocity of water increases the fluctuations in the stream of dye until the stream of dye gets mixed up completely with water in the tube. Still further increase in velocity of flow does not cause alteration in the type of flow. In this type of flow, the path of individual particles of fluid are no longer straight everywhere, but are sinuous, intertwining, and crossing each other in a disorderly manner, so that a thorough mixing of fluid takes place, and such a flow is called turbulent flow. Let us calculate the velocity of flow. Now, let us decrease the velocity of flow in the glass tube till the stream of dye is again visible in the glass tube. We find that the velocity at which the change from laminar flow to turbulent flow occurs is higher than that which caused the change from turbulent to laminar flow. Rynolds called these velocities respectively the higher and lower critical velocities. Rynolds also found that the nature of flow, that is, whether laminar or turbulent, and its relative position along a scale, indicating the relative importance of turbulent to laminar tendencies, was indicated by a dimensionless parameter which is called Rynolds number. This dimensionless parameter is given by Rynolds number is equal to rho LV over mu, where rho is the mean density of fluid, L is a characteristic dimension of stream. For example, in this case, L is the inside diameter of pipe. V is the velocity of flow, and mu is the coefficient of dynamic viscosity of fluid. Expression for Rynolds number can thus be expressed as ratio of forces. We find that this dimensionless parameter represents the ratio of inertial force to viscous force. At low Rynolds number, the viscous forces predominate and the flow is laminar. At higher values of Rynolds number, the inertial forces overcome the viscous forces, and consequently, the fluid layers break up into turbulent flow. It has been found that for Rynolds number less than 2000, the flow is always laminar. Under ordinary conditions, transition from laminar flow to turbulent flow takes place for Rynolds number 2000 to 3000, and for Rynolds number greater than 3000, the flow will be turbulent. More recently, however, it has been proved that the magnitude of Rynolds number at which laminar flow becomes unstable depends largely upon the nature of disturbance present in the flow. For example, critical values of Rynolds number over 40,000 have since been reached with Rynolds' original equipment, largely as a result of increasing the stilling time, improving the rounding of the inlet, and eliminating all possible vibrations. Thus, the maximum value of Rynolds number at which laminar flow is physically possible appears to be indeterminate. The disturbance necessary to produce instability simply decreasing in magnitude as Rynolds number becomes larger. For most industrial applications, the critical Rynolds number lies between 2000 to 2300. Rynolds number is applicable for all flow conditions, laminar or turbulent, where the viscous nature of fluid is considered. Rynolds number is the principal parameter determining the nature of flow when studying the motion of bodies in a fluid of large extent of flow or fluid around such bodies. It helps in the study of forces on tall buildings, telegraph poles, etc., due to high velocity of wind, problems of motions of automobiles, aeroplanes, submarines, problem of separation, eddy formation, and lateral mixing in flow through abrupt contractions, abrupt enlargements, abrupt inlets in pipelines, and also due to abrupt obstruction in flow. settlement of solids in a liquid, problem of heat transfer, problem of sediment transport in rivers, etc., loss of head in pipeline, problems of lubrication of machine. Thus, to summarize, viscosity is one of the very important factors affecting the flow of fluids. It is the property of fluids by virtue of which fluids resist relative motion between adjacent layers. Osborne-Rynolds formulated a parameter, now called Rynolds number, to take into account the effect of viscosity. Rynolds number is a dimensionless parameter and can be seen to be the ratio of inertial forces causing flow to viscous forces resisting flow, and is given by rho into L into V divided by mu. Whether the flow is laminar or turbulent is determined by the value of Rynolds number. At higher values of Rynolds number, the inertial forces overcome viscous forces and the flow is turbulent. But at lower values of Rynolds number, viscous forces predominate and the flow is laminar. For Rynolds number less than 2000, the flow is always laminar. Transition from laminar flow to turbulent flow takes place for Rynolds number 2000 to 3000. For Rynolds number greater than 3000, the flow will be turbulent. This upper critical value of Rynolds number depends largely on the nature of disturbance present in the flow. Rynolds number is an important parameter used in the analysis of fluid flow problems such as flow in conduits, flow through porous media, design of automobiles, aircrafts, missiles, harbors, turbines, water distribution systems, and irrigation canal.